Yeah, we're very happy to have Valentin and Bortoli from Google DeepMind here.
Yeah, thanks a lot for the invitation. And yeah, so this afternoon I just wanted to chat a little bit about some work that I did actually last year, and then we have a follow-up this year because I've obsessed a little bit about this, and it's relatively simple, like from a methodological and theoretical point of view, but like I hope it's something interesting and like it sparks a little bit of discussion in terms of like some of the basis that we have on some basic knowledge that we have on diffusion model. So this is joint work with a bunch of people, both at Google DeepMind and also in Munich, especially the latest part of the work has been carried down by Tommaso. So what I want to talk about today is this new way of defining, like kind of an extension of diffusion models that we have that we call distributional diffusion models. And I kind of want to explain one and really highlight one of the limitation, like current limitation from a more maybe engineering perspective on diffusion model. And then try to see like, okay, how can we try to mitigate that and what has been tried in the literature and like what is our proposal there. So of course our proposal is distributional diffusion model. Something I do want to talk a little bit about, and I'll see if I have time to do so, is how to scale those models, because most of the time, and it's something that comes up quite often, like things will work well on like Sci-Far and now maybe even ImageNet, but it's really hard to go past that and like have methods that are robust to scale. And so it brings up a lot of questions, both from the architecture perspective, but I think also from methodology perspective. And I'll try to comment a little bit about what is done in the literature for this. All right, so I'm going to be very quick on that, but like I think I do want to reintroduce some of the formalism here because that's going to be very useful for me later on to try to explain like the limitations that I'm trying to address. Okay, so everyone knows here, diffusion model. You start from real data and you go to a noise sample. So this morning when we had some of the theoretical talk, like most of the time now, I would say one of the preferred view on diffusion model, at least to introduce them theoretically, and I used to introduce them like that too, is with a continuous time dynamic. Because with a continuous time dynamic, like you kind of like bypass a lot of the discretization problem, and it also shows, like reveals some of the structure that like you only need to learn the score, and so that's really nice because the score is a conditional expectation, and then you can use 3D formula, and then you can unroll the whole story that we usually have. But like what we're going to do in practice, of course, we're going to discretize all of this. And then usually we do the jump by saying, right, so we have this SD or this OD, and then we use whatever discretization technique that we have. Okay, but I just want to show that like there is like a very simple orthogonal way to think about it, and it's usually when you're going to implement a model, a diffusion model, you're going to start by just saying, right, I'm going to define my noising mechanism. So like you just have those two coefficients, alpha t and sigma t, and you just have the condition that like alpha 0 is equal to 1, alpha 1 is equal to 0, sigma 0 is equal to 0, and sigma 1 is equal to 1. I'm taking the diffusion model convention. I'll stand by this, that like x0 has to be the data. So that's how you define the noising mechanism. And when the usual thing that like you are going to do is then you're going to say, okay, how do we go back in time, right? And so how do we go back in time? We start from pure noise. Usually Gaussian. So by the way, like all of what I'm talking about, I'm going to stick to the Euclidean setting. In particular, everything here is like Gaussian in RD, like everything is really nice. I will discuss at some point like some extensions to what we can do in the Riemannian setting and in the discrete setting. The reason why I'm not talking about it now is just for simplicity. Right, so we say we start from this nice Gaussian, and then we define those backward transition. And in a way, like this is very simple, but like the only thing that you need is you need to say, okay, how do I go from xt to xs? And you can decompose that into 2 bits, this jump here. You can decompose it into like, okay, assuming that I know what xt, which I do, and assuming that I know x0, then how do I get xs? And this is just a simple interpolation formula, right? Like, and usually for this, we'll see that like this is really nicely done with like just a Gaussian interpolation. Yeah. Of course, now the hard bit is like, given xt, I need to be able to predict x0, which sounds like I am kind of restating the original problem. If I want to do generative modeling, I want to model P of x0. Now I'm just saying, okay, I want to model P of x0 given xt. So like I'm kind of like not doing anything. The important bit here is, of course, that like now I have this conditioning xt here, and that's going to be like really useful for me because now I can train a model to kind of like, given the knowledge that I have in xt, I can try to predict what I have in x0, right? That's kind of the whole purpose. But like, I just wanted to highlight again that like there is a part that here that is given by the interpolation, that is given by the schedule, etc. And this part here is just like how well can I predict x0 given my xt. All right. So of course, now if you try to define, so this is where you are now, and then you can say, right, so this part, like you're probably gonna feel that you're gonna learn this part, but then this thing actually you can derive, exactly, like you can derive an exact formula for this if you impose the consistency condition, which is that like, okay, now if I want to look at my marginal P of S of xs, I want this to be what? I want this to be, I want this P of xs, P of PS of xs to be equal to this marginal here, okay? So that means that if I sample x0 and xt, and then I have my x0 and xt that can come from the forward process now, like if I'm using this interpolation formula, then like I will end up at P of xs, okay? Maybe another way of writing this down to really highlight the fact that like this thing is actually very simple, is that you can rewrite the same consistency equation, because this will ensure that like if you are at P of xt, then when you're gonna jump, and if the P of x0 given xt is perfect, this will ensure that like you stay at P of xs, right? So this consistency equation here, this is just to say, right, if I have a perfect prediction, how do I define this thing so that I stay on the forward path? That's really just all it says, okay? So here again, like I'm not discussing the SDE or the ODE interpretation, but like of course all of this is related. I'll explain how. Yeah.
This is something like condition on x0 and xs is independent of xt, no?
So
the purple one that you have seems
yes.
P of x.
Yeah, I mean, like this is what I'm like. This is if you yes. So totally right. If you one choice is to use the forward, right? So the forward is just P of x, P of xs given x0. Yeah. Like here, I'm just saying like I'm trying to find a family of distribution that satisfies this equation. So one.
You're saying that the one that we are familiar with is just one instant.
Yeah, so the one that you're talking about, this P of xs given x0, what it would give for you in the algorithm that you have here, so that means that like here you're just basically dropping the dependency in xt here. And so what it just means is you are at xt, you predict x0 with that thing here, and then now you go to xs by just using the forward, and you drop the dependency in xt. And like this thing, like now if you feel that like, okay, you can play with like how much dependency with respect to xt you put in there. So the one that you're describing is the extreme case where like you completely forget about xt, and this is what the churn parameter usually does. And if you think about what happened in discrete diffusion model, this is exactly what remasking will do basically. So yeah. So this is totally valid. But like what I'm trying to, something I should have said is that like here when I designed this, I only gave to myself the P of xt given x0, and like I didn't give myself like a full trajectory. I just have a bunch of P of xt given x0, and now I'm trying to find a probability distribution, P of xs given x0 and xt, that satisfies the consistency equation here. And there are many choices. And like exactly what you're saying, one possible choice, so you can find a whole family of like Gaussian that is going to satisfy this thing. And by the way, this is exactly what DDIM is doing. DDIM is doing that, but like you see that like you have a free parameter, which I call like, I call it epsilon. I shouldn't call it this way, but anyway, epsilon is the churn parameter, and epsilon, if you play with that epsilon, you can put, I forgot what is the value here, but like you can put the value of epsilon so that you recover exactly what you're saying. So basically what it means, actually I think I can find it. It's so you always have that like this P of xs given x0 and xt is a Gaussian. And so now you look at the mean. The mean is like some linear combination between xt and x0. And you can just define epsilon here so that like basically this term is 0. And then if you do that, you realize that like, okay, this whole thing is P of xs given x0. So like, like depending on like this churn parameter, like you can define like a whole family of those things. So I always find it like a useful way. Yeah?
In general, this P of S0t doesn't need to be Gaussian.
No, yeah. We just use it because like it's nice to implement, but yeah, for sure. Like, it's just a small subset of the solution. And actually, you could say that like if your prediction is bad, like maybe you would like to try to maybe not use a Gaussian there. Like it's, 100%. Right. Other question? Okay. So, right. So basically, so we spent a little bit of time on this term, but like I hope you can more or less trust me that like I can define this thing in a Gaussian way that depends only on the schedule and some hyperparameter in a way that like if this thing was like perfect, if this prediction was perfect, then I would satisfy my consistency equation and I could just roll back the diffusion model, right? And something I should have said as well is that like if you look, I have the derivation in the paper. You will have to trust me for this one, but you can imagine that like, okay, like how do we go back to the SDE and like how do we go back to the ODE? Well, you can take here, if S is close to T, like you take T, which is equal to S minus H with like H infinitesimally small, and then you write down what is the expansion, and you look at the mean and you look at the variance, and then that will give you like, some kind of discretization of an SDE, and the term that you recover are exactly the backward SDE that you would have, or the backward ODE, because again, this thing also covers the fact that like, one way you can do the conversion between SDE and ODE in diffusion model is that you just play around with like Fokker-Planck, but like here you can see that like now if you choose the epsilon to make this term go to 0, then you have no covariance at all, and then your things becomes like a deterministic update. And if you have a deterministic update, then you recover DOD stuff. So that's just another way of looking at things. But I like this part because like it really highlights what we do in practice, which is that like we start with the discretized version, and we need to do those jumps. Right. Okay. So the whole point of diffusion model then is to say, right, okay, now I'm given this, so either DDIM, whatever discretization, blah, 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 blah. This thing depends only on the schedule. Now, what I'm going to use for this? And the beauty of diffusion model and like why they work so well is to say, right, like if S is very, very close to T, actually this thing doesn't really matter. Like the whole posterior doesn't really matter. What really matters, like all of this concentrate, and like if you look at the SDE, that's what we were talking about before, it gives you the score, and so the score is just like related to the conditional expectation of x0 given xt, and so you just have a conditional. Instead of having the whole posterior to cover, you just have the conditional expectation to cover, to approximate, which is like much easier because now like if you say, okay, my approximation is just this Dirac mass, then like you can say, right, so I'm just going to approximate that with the conditional mean. And that's one way to see diffusion model. But of course, like this is only true, this kind of approximation is only going to be valid if S is infinitesimally close to T and if we have the SD interpretation. Again, usually in practice, what we do is we do larger jump, or at least we wish we could do large jump, which implies that like this approximation is no longer true anymore, and we will need to do something better here. And that's the whole motivation for the distributional diffusion model. Right, so just to summarize quickly here, when we do diffusion model, wait, okay, sorry, there's a word missing. We only want to, the diffusion model will only require the conditional mean approximation, and the approximation is valid only for a large number, like when I say number of function evaluation, you can think of it as like S is close to T because I have like many steps, right? Okay, so, and then we have the classical thing that like if we have a better approximation, I can use more step and I have like slower sampling. And now what I want to present is like, okay, of course this is very problematic when I'm going to try to serve my model, etc. There are many solutions to kind of like alleviate this. We'll explain a few, but like I will also explain why distributional diffusion model is fine. All right. So, just a small detour through scoring rule. So remember that like what we're trying to approximate is really these posteriors, this P of x0 given xt. Okay. So again, during this P of x0 given xt, I'm going to state a few conditions on what I'm trying to do. They're more vibe-based than like anything really mathematical here. But like when you think about it, okay, how can I approximate this posterior P of x0 given xt? Well, you could say, right, like one way to do that is like I'm going to do another condition. I'm going to do another diffusion model, right? Another diffusion model to approximate this P of x0 given xt. There's going to be now condition on xt. So I'm not trying to learn the unconditional P of x0. I'm trying to learn the conditional P of x0 given xt. This is exactly what GlassFlow, I don't know if you've heard of that paper, what GlassFlow does is something like that. And then their flow map version, MetaFlow map, will do something like that as well. The problem is that it also requires, like going the whole GlassFlow way, you require like many function evaluation. So I kind of want to have like an approximation of that P of x0 given xt. I want to have that in like ideally one function evaluation. Okay? I know it's not really possible, but that's like what I'm aiming for. Another thing you could say is that like, okay, well, learning P of x0 given xt, you could use like things like GANs or any adversarial method to do that. And yes, that's a very valid answer. And actually, a lot of the distillation methods that exist currently for diffusion model, they do use some kind of adversarial-based technique to like try to reduce the number of function evaluation. The problem is that like implementing GANs at scale is very finicky. They tend to collapse quite a lot. And overall, it's like, it can be quite painful to do. So like if we can avoid using GAN, we prefer to do so. And something also that we would like to have is if we can train something that is like very close to the loss of a diffusion model, we prefer that just again for scaling reason, because if we're close to diffusion model, we already know how they behave and how they work at scale. So all of that to say that like now that you have kind of like all those vibe constraints in your head, one thing that we started to think of was like, okay, there is this thing called, actually, this is kind of like the general framework. You will see like we started from the example that is on the next slide. Something that kind of works is to define, let's say I define a proper kernel, like if I have a kernel function, again, defined on the Euclidean space RD, if I manage to define this thing here, so this score between P and Q. So here now, like I'm just back with like two general distribution P and Q. I'm trying to minimize that and try to make it so that P is equal to that. Find a loss function such that this SPQ is always lower than SQQ. I'm sorry, I don't know why the scoring rule literature is always with a minus compared to the last one, which I find very confusing. But yeah, with like this is what you want as a property. You want that SPQ is less than SQQ with equality if and only if P is equal to Q. And one way to do this is like if you define a kernel that is proper, strictly proper, you can have that. So basically what you will have, I will again explain on a specific example on the next slide. But basically you have like two terms. You will have one term that is going to compute the kernel between X, where X is sampled from P, and Y, where Y is sampled from Q. And you have like another term that is going to depend on like the interaction between P and Q. Okay? So the thing that you define at the end of the day is you're gonna define this object here, okay? Which is just so you can think of rho as a kernel. Again, I will go and give like the concrete example of that. But you can define this interaction term minus this term, where like here you're trying to map X to Y, and you take the expectation of a P. In the next slide, we'll take also the expectation of a Y. And once you have this thing, this is what we call a kernel score. So here, I just go a little bit further. I'm also introducing this hyperparameter lambda. In practice, in theory, you should take lambda equal 1 to have a proper scoring rule, but I'll show why for me it's useful to have this freedom of having the lambda. Of course, if lambda is not equal to 1, I lose like all the nice properties that like this property is only true for lambda is equal 1. Okay, so just bear with me one more slide. Now, like let's say that I have such a kernel. Okay, one kernel, specific kernel that I'm going to choose, and you will see why it's like super nice for us, is what we call the energy distance kernel. So the energy distance kernel is just defined between x and x prime. This is just the norm between x minus x prime to the power beta with, and I didn't write it on the slide, of course, with beta strictly less than 2. Okay, so beta is between strictly greater than 0 and strictly less than 2. Okay. And if you have that, beta strictly less than 2 and greater than 0, you will define a proper scoring rule, and you will define a loss function such that like you have SPQ, which is always less than SQQ with equality only if P is equal to Q. All right. Yeah.
Just to be sure, here your assumption of K is that K is PSD?
Yes. Yeah, exactly. I know the proof only in the case of the energy distance kernel, and for the general proof, I will have to invoke Arthur Gretton, who is not here. But yeah, the proof for this is actually quite nice. Yeah.
So the beta is negative or positive?
It's positive. It's positive. It's strictly between 0 and 2. The strict is important. Like if you get beta equal 2, this is no longer true. Yeah. So if you look at what you end up with, just to recall, the diffusion model loss was just this L2 loss, right? Okay. By the way, I'm writing the diffusion in the previous talk. We were talking about velocity matching. You know that like you have all these different parameterization for diffusion model. Here I'm choosing the X0 parameterization because it makes my life easier. So the diffusion model loss, I can always write it as like this X0, this L2 regression loss. Now I'm just saying, right, I'm just going to swap that for the scoring rule here. And so what I end up with, if I replace that by the scoring rule, you can just kind of forget about this general formula. You can forget about this, and you can just look at what you have here, which is basically, and again, apologies because here there is a minus, so like think of this with like the minus in the front. So what you have is that you have a first term, and this first term looks really a lot like this one. The only difference that we have is that this, I don't have a 2 here, I have a beta. Okay, that's literally the only difference. And the nice thing as well is that I have another, well, the new thing now is that I have another term here, which is just, which like has the opposite sign as this one, which is just telling you, right, if I sample if I'm at my XT and I'm sampling a bunch of proposal, I'm going to try to make them far away. Okay, so just from a very intuitive perspective, and this is why I kind of like explaining things with the energy distance here. The energy distance is kind of like you look at the diffusion model loss, you tweak it a little bit to not use beta equal 2, but beta strictly less than 2, and you add another term which will enforce some kind of repulsion. And you can think of it as like, okay, if I only had, again, this is just to give you some vibe explanation here. If you only had this term, then you will collapse on the conditional mean if beta was equal to 2. Now beta is not equal to 2, and I also have this term that is like trying to push the samples far away from each other. And magically, like all of those things balance, and I'm modeling the whole posterior instead, if things were perfect. Yeah.
So in the denoising diffusion model, we have this score interpretation of denoiser. Here, what will happen? Is it the score times
yeah.
inverse of the...
Well, it's a good question actually. So here, I mean, I know that the minimizer, if lambda is equal to 1, I know it's the whole posterior. So that's in diffusion model, you will have the minimizer will be the conditional mean. Here it will be like, so something that I have to say is that like in diffusion model, that thing is like deterministic, right? You have like, it's a point estimate. Now what I have here, well, I'm going to parameterize that is something that is like stochastic, right? Otherwise I cannot model the posterior. So you can think, I mean, in a way you can think of it as like, this is gonna be the conditional mean plus a stochastic term that is basically accounting for the whole posterior, if that kind of makes sense. Yeah. Yeah, like something that maybe might help to understand is like, of course, you cannot, the same thing as in diffusion model in general, you cannot do like explicit calculation, but I always find it like quite informative to just try to see what it would give you, minimizing this loss in the context of like where your target is just a simple Gaussian with like just mean that is mu and variance is sigma square here. Let's say that everything is in 1D, and then you consider P, like this thing, P of x0 given xt, to be the Gaussian minimizer of this thing. So again, the minimizer of this is probably not Gaussian, but like let's say that you restrict yourself to the Gaussian minimizer just because it makes like all the computation easier. And then once you have that, you can try to see, okay, now I'm going to look at the inference, and I'm going to look at like what are the steps that like what is the distribution that I'm tracking at every step of the inference, and you see that like you can write every time it's going to be Gaussian because I made it so, like all the terms are Gaussian, and you can compute what is the mean and what is the variance of that Gaussian, and you see that like it is the mean is independent of lambda and beta, so that should tell you something. Like that is telling you that like basically tracking the mean, you're already doing that very well with diffusion model. What was missing in diffusion model was tracking the variance term. And like you have a modulation term now that depends on lambda and beta, the hyperparameter that I have. If lambda is equal to 1, this term here is equal to 1. And you will see that like actually this is the exact formula that you need to really recover that like at time 0 you have the exact data distribution, and as soon as this lambda is strictly less than 1 or this beta is equal to 2, this term is going to move around. So like this is a small plot of that term here, and you will like start to fall back to diffusion model where you accurately track the mean, but like you fail to track the variance. Another thing that is like also quite interesting there is that you're like, right, okay, but you said before that like if everything was perfect, the ODE or the SDE, whatever, should bring you back to the data distribution, and that's indeed the case. If you take S close to T, so again, like I'm hiding a lot of terms here. I'm hiding all of the term for simplicity in those things. But if you take S close to T, you see that like this term, like when you do the Taylor expansion, the only term that matter are this one, and this one is of a higher order, and so basically it disappears. And so that means that like in fact, when you are taking a large NFE, the effect of choosing properly a proper scoring rule kind of goes away. I don't know if that clarifies things. So in a sense that the thing that I'm talking about only matters if you are trying to do big jumps. If you're fine with doing, SDE, then like you can stop listening, I guess. All right. So yeah, I mean that's the whole, like in terms of methodology, that's kind of like where we, yeah. Sorry?
Have you thought about how to do the parameterization or not yet?
The lambda and the beta?
No, like how do you train peep data of like a distribution?
Yeah. That's 2 slides.
Great.
Yeah. But yeah, indeed, no, but you're right. It's like, right, so now, okay, how do we have that, right? So basically what I'm saying is that something that you could do is that you can replace this capital X here, you replace that by like a generator, kind of like the same way you do in diffusion model. Of course, as I was saying, like you cannot have something deterministic, because if you had something deterministic, like this thing will collapse and you cannot model the posterior. So you need to inject some kind of exogenous noise. And that is a hard thing to do, actually, from an architectural point of view. All right. So this is exactly what I'm going to talk about. So the way we inject the noise is by doing the following. So we say, right, now the model is going to depend on the time, on xt, and on some exogenous noise that usually we just sample a Gaussian that has the same shape as xt, and we just try to pass that to the network somehow. And fingers crossed, we hope for the best and for the transformer to do its thing. Of course, if we do that, then like the cost of doing that is, instead of having, if you just concatenate things at the beginning, what will happen is that like each forward pass through the network will be twice as costly. And so this is kind of like unacceptable, because that means that like training a distributional diffusion model, it becomes like twice as expensive as training a diffusion model. And like at the scale that we're talking about, it's like if your training run goes from 1 month to 2 months, it's like not acceptable at all. So something that we do is like to reduce that cost, we only inject the noise for the later part of the transformer. So for example, like something that we have in the paper is like if we have 28 layers, we only inject it for the last 4, and then like hope that this will be sufficient to steer the model to like learn the full coverage of the distribution. Of course, we're always operating in the regime, like we know that's not going to be perfect, especially for like very large scale image net or text to image model, but we have to take those constraints into consideration. Yeah, so another thing that like I have to say, I'm going to maybe skip this thing, is like, okay, how do you inject the noise as well? This like matters a lot, and like if you've been following some kind of architectural consideration on diffusion model, that's something where like there is a lot of know-how that goes into this, and so we explore a lot of those alternatives. Something that we found to work quite well, I don't know if it's something that is like quite general or not, is just appending it to the current input. But then when you have your transformer layer, you do not multiply the dimension by 2. Like you just assume that like, okay, the input is gonna have dimension 2D on terms of channels, and then I'm just gonna pretend that they have like when I'm gonna have my first MLP is gonna contract things by a factor 2. I'm gonna do my whole transformer layer, and at the end I will just expand by 2 again. So you just have a factor 2 on the residual stream. Yeah, and something as well that like we noticed is that something that helps a lot is this approximation that I'm saying, right, approximating the posterior, it doesn't matter uniformly on the diffusion trajectory. So there are parts, for example, you can imagine that like now, when t is close to 0, this p of x0 given xt, well, it's not a bad approximation to have that approximated as a Dirac mass, right? Because like when t is close to 0, that thing is already super concentrated. So the intuition that you might have is that, okay, when you are far away from the target, like so close to the noise, it makes sense to try to have something that is like more like a posterior that is trying to cover more the posterior. But like as you get closer and closer, it's fine to go back to the diffusion behavior. And we actually found that like this helped the training quite a lot in terms of like efficiency. Yeah.
Can you also adaptively decide whether to inject noise in the architecture or not? Also based on like the steps? Like you mentioned you add the noise only in previous layers. Could you also start to say complete?
Yeah. So yeah, that's a good point. So basically you're saying that like based on the time of the diffusion, you inject it like earlier or like later?
Yeah. Since everything's a transformer, like in principle.
Yeah, no, yeah, you're right, yeah. Yeah, no, that should be doable. Yeah, we didn't do it, yeah. But so something that we try to sweep a lot on those things here, trying to understand what was the best choice. We found that like it's better to inject it like later. Actually, the best thing is like to inject it like just in the middle, but then like, I don't know, it becomes like, yeah, it's basically like depends on your problem. But yeah, I think that's a good point, what you're saying actually. So you would inject it like earlier for the earlier time. Sorry, for the time close to the noise, so that you have like more noise information, and then as you get closer, yeah, that makes a lot of sense actually. Yeah, I mean here I'm gonna skip that, but like basically like we try to be like very rigorous for this. Like this is the fit score, the lower is better on ImageNet, and we try to show that like really when we add all those components, this is what really gives us something that like has good performance for a lot of time steps. So like 4 time steps is like you just do only 4 jumps to get to the target, and that has a training cost that is like reasonable. I'm not going to dive into the detail for this. I'm gonna be quick here again. Again, same result. Here we are looking at the fit score on the y-axis. X-axis is the number of diffusion steps that you use at inference. Something that like we are particularly interested in is that in the low NFE regime, if you look at the low NFE regime, the one that is going to win is when you use lambda equal 1 and beta strictly less than 2, which is exactly the case of the scoring rule. So like there is some indication that like in low NFE, the diffusion objective is not the best one. And like we only changed the diffusion objective and the architecture a little bit. Of course, like when you start increasing the number of function evaluation, then the diffusion baseline starts to win, and like at 100 steps, basically the diffusion is better. Some behavior that we found that was quite weird, and I don't have a really good explanation, is that if you use the proper scoring rule, it does slightly worse than the diffusion baseline. So, which is like, okay, you do not really expect that. You would expect it to do like similarly, or like why is there some loss? We think it's due to the training dynamic. We partially fixed that with like all the stuff that I was talking about in the previous slides. This is like without all those tricks on like some small scale stuff. But I think it's interesting to it would be interesting to try to understand the training dynamic of those things. I'm gonna skip that. And yeah, so again, this is just to showcase that like with all the improvement that I talked about, you can scale it to like 4 steps on ImageNet and have like very decent results. But those days, ImageNet is not enough because you can train like a lot of methods in like 1 step on ImageNet, and they are really, really, really good. This is ImageNet 256. So something that we went a little bit further than that, and we went to text to image. And I just wanted to include that slide just to say that like if you're working on image generation, now like like when I started my PhD, like a paper with like Sci-Fi was like good. You could get published with that. But I think like now the bar has increased significantly, and like people will ask for like fit score or FDR score on ImageNet. But even that, when you look at some papers now out there, it is kind of like easy to game ImageNet and a very, very low fit score. And then you see that method, is never used, and it's because ImageNet is a very specific data set. It has like very, the conditioning is like a bunch of classes. It's like a very strict conditioning. In practice, when you're gonna have production model, the conditioning information is like much, much richer. And you cannot have a lot of the tricks that are specific to ImageNet, like have like dedicated pipeline for the data or stuff like that. So a really good test is like, does your method scale to like text to image? And it's a really good signal if like, okay, the benefits are gonna stay there at scale. So that's like, we spend quite a lot of time, well, Tommaso spent a lot of time scaling things to text to image. It does work, so this is 16 steps, and the images are 512 by 512. And yeah, I mean, this is just to showcase one result and also to kind of like raise the attention to the fact that like, yeah, probably now text to image is something that like people should think about because the text at the bottom is the conditioning. So like you have like much richer conditioning than what we were having before.
Can you share your intuition again? Why is conditioning make things harder?
Yeah, I mean, it's just that like yes and no. If you have a very strong conditioning, then like you have like basically one image per conditioning. So it's just like you could, like you almost have a distribution collapse, right? But at the same time, you have a model that has to be able to understand like a bunch of very different conditioning. And for example, something that that's perfect, I'm on this slide. So if you've looked at like drifting models, they're required to have like a huge batch size for them to work. And so it's a huge batch size per conditioning. So it works for ImageNet because like, if you have like Malamute, like you can take all the Malamute and you find like 1,000 of them, and that's, you can put that in your batch. Now, if I have, natural text, I cannot do that anymore. And so it's much harder to get like repetition given for a given conditioning. So yeah, that's one thing that like makes a lot of the methods that like, a lot of the methods that are based on particles, like what I'm explaining right now, a lot of them, and ours is also kind of sensitive to that. Like, so this is clearly one of the limitations that we also have to mitigate. Is that you really rely on like huge byte size per conditioning, and that is problematic. Yeah. So just here, like this slide, I don't know if you're terminally online like me, you've seen like all the controversy around that new paper. But basically, like there are a bunch of other methods that have appeared this last year and this year and this year that also kind of like try to go beyond diffusion model. And I feel like there is kind of like this feeling that like all of them either use some kind of version of using like a bunch of particles from the thing that you're trying to generate. So actually, inductive random matching is very close to ours. It's like kind of like doing the consistency trajectory model version of like what we did. Drifting also use a bunch of like particle, and it has an interpretation in terms of fixed point of a gradient. I think the talk after me is actually going to talk about drifting models, so that's perfect. And this one is like very close to this thing called implicit maximum likelihood, where you also need a bunch of generation. So yeah, this is just to point out that like there is all this literature that is related to this. I'm just going to conclude very quickly, just to summarize. Like I think that there is one point of diffusion model that we have kind of, like that we do not often consider because the regression loss is like so nice to have, which is that like really what we really would like to do is estimate the posterior. And that would unlock, if we were able to do that at scale, it would unlock a lot of things, especially in low NFE regime. So something I want to say is that like what I'm proposing is just like one way to do this. Like you don't have to go for the scoring rule way. I think right now, distillation methods, like I haven't talked about like mean flow and stuff like that, or moment matching distillation, like they are really, really good. The problem is that they do not model the posterior, so that's what we're trying to do as well. We're trying to propose something that's like a bit orthogonal. I was honestly quite surprised to see it scale to like text-to-image model, so like congrats to Tommaso for that. And yeah, I think like this is thinking about modeling the posterior is something that like we should think more about, especially if we move to a regime where like we really want to have good coverage of the distribution, like like we want really to cover the distribution tails, like for example in RL and stuff like that. Something I will conclude with is that I've tried to think of like how to do this in the discrete diffusion model setting, and I have nothing that I've think of like has worked so far. So if anyone has an idea, I think like there is some opportunity there. I think the Riemannian setting would be a tiny bit easier there. But yeah, that's pretty much it for me. And yeah, thank you.
So I have one question. Can we use the score estimated by diffusion model and use it as a, to design our kernel?
To design the kernel. Yeah.
It's like the Stein. So what is it? This variation?
Yeah. I do. Yeah. Yeah, some Kernel-Stein discrepancy stuff. Yeah, probably. Yeah. Yeah. To be fair, we didn't really investigate. I mean, we tried so I can tell you which kernel we tried. We tried all the kernels all those kernels. We tried all of them. But they all they're agnostic of the target. I think indeed either being able to learn the feature of the kernel or using the score directly is something that's definitely doable. The reason why I was advocating, and Arthur really wanted to push in that direction, the reason why I advocated against it is because I really wanted to stay close to the diffusion model framework where we have something that's very simple and we can just extend it. But yeah, I agree. Yeah.
Oh, quick question. Maybe I missed it, but what is the advantage of something like this over, say, a flow map?
Yeah, so that's a really valid question. So the flow map, again, you're going to have a deterministic estimator. Here, we're really trying to cover the whole distribution. We're trying to cover the P of x0 given xt. So the thing that would be equivalent is metaflow map. Metaflow map, you're really conditioning on this.
Yes, yeah. I agree there's a difference in what you're modeling, but I mean, just at an empirical level, what is the advantage of doing posterior sampling if a flow map will already give me?
Yeah, no, I mean, to be fair, I don't have the good perfect answer for that. I think right now we have compared it to metaflow map. So metaflow map, when the results that are reported, they are starting from a pre-trained flow map model, whereas everything that I've shown is trained from scratch. So I have to say that I don't have a apple-to-apple comparison. When we've tried to train the metaflow map from scratch, it was really not good. So we are not sure if we're doing something that's why I don't want to say that metaflow map is not good, because it might be a skill issue on our end to train the meta flow map. But yeah, there is nothing. In theory, there is nothing that we can do that the metaflow map cannot do, and vice versa. Yeah, it's just orthogonal stuff. Yeah.
Okay, one more quick question. If not, then let's thank Valentin again.